Imagine trying to win a gold medal at the International Mathematical Olympiad. I mean, the reigning assumption in the ML community right now is that, well, to pull that off, you need a model the size of a small city.
Right, yeah. Like half a trillion parameters.
Exactly, a massive mixture of experts architecture, a computing cluster that could, power a neighborhood just to brute force the logic.
And that assumption of scale has driven almost all recent research. We've seen systems achieve that silver or gold medal standard, but
But it almost always comes with an astronomical search budget.
yeah, paired with a massive underlying backbone. The paradigm has essentially been, scale the parameters to scale the reasoning.
Well, today we are taking a deep dive into a recent ArcSev preprint that completely upends that paradigm. The paper is titled Achieving Gold Medal Level Olympiad Reasoning via Simple and Unified Scaling.
And it's a massive collaborative effort.
Really is. It's from researchers across the Shanghai AI Laboratory, the Chinese University of Hong Kong, Tsinghua University, Shanghai Jiao Tom University, and Peking University.
Wow, that is quite the roster.
Yeah. So for you, as ML practitioners, data scientists, and mathematicians listening to this, our mission today is to bypass all the hype. We are going to meticulously unpack the technical architecture and the training methodologies behind SU01.
Which is a surprisingly compact model.
Right. It's a 30 billion parameter model that actually achieved gold medal level performance on both the IMO and the International Physics Olympiad.
The engineering here is just incredibly elegant. I mean, the researchers utilize this unified training recipe that moves from supervised fine-tuning to a highly specialized two-stage reinforcement learning pipeline.
And finally into test time scaling.
Exactly. And they operated under what they call the specializable generalist hypothesis.
Okay, so meaning what exactly?
Meaning the goal was not to build a narrow, brittle solver that, only knows math. They took a broadly capable scientific model and explicitly specialized its proof reasoning behavior.
Without stripping away its broad scientific competence.
Right, exactly.
Okay, let's unpack this. Because before they could even think about scaling the reasoning with RL, they had to tackle a fundamental behavioral problem, right?
Oh, absolutely.
I mean, you can't just take a standard post-trained model and ask it to write an Olympiad-level proof. It doesn't know how to structure that kind of rigorous search. So they didn't build this from scratch. They started with an existing backbone. How did they actually force it to change its behavior?
Well, they started with P130B A3B.
Okay.
That is a post-trained model that's already competent in general scientific tasks. But, like you mentioned, it was essentially just an instruction follower.
Right, so if you ask it a really hard question.
If you ask it to solve a complex IMO proof, it just falls back on shallow heuristics. It will circle around the same intermediate claims or just generate an endless loop of reasoning without ever making decisive progress.
It just spins its wheels.
Exactly. So to fundamentally alter that behavior, the team curated a supervised fine-tuning, or SFT, mixture of 338,000 filtered trajectories.
And what kind of data actually makes up those trajectories? Like, are we just feeding it textbook proofs?
No, it is a mix of math, STEM, code, and instruction following. But the crucial part is how they augmented it.
Oh, okay.
They heavily populated this data set with self-verification and self-refinement traces generated by a much larger model, specifically DeepSeek v3.2 Special.
So they're using a bigger model to show the smaller model what good reasoning looks like.
Yeah, exactly. And they also put a hard cap on these trajectories at 8,192 tokens to avoid optimization instability early in the training.
There's a massive hurdle here, though.
Yeah.
When you force a post-trained model to learn a completely new, highly verbose, long-form reasoning style, it usually suffers from what the literature calls long-caught degradation.
Right, catastrophic forgetting.
Yeah, the network effectively overwrites its existing knowledge just to accommodate the new formatting. How did they avoid that?
That is the most delicate part of the behavioral shift. I mean, you are trying to rewrite the routing and attention patterns of a model that already knows science. But it doesn't know how to format a rigorous proof. If your SFT signal is too narrow, you basically destroy the pre-trained knowledge.
So what's the fix?
To solve this, the researchers implemented a reverse-perplexity curriculum.
Okay, I love this concept from an optimization standpoint. To put it simply, it's like making a student eat their vegetables before they get dessert.
Yeah, that's one way to put it.
You force the network to process the most unfamiliar, confusing proof patterns first, before it's allowed to settle into the easy, familiar examples. In ML terms, it's essentially a temperature schedule in simulated annealing.
That is a perfect way to visualize it.
Yeah.
Mechanically, They score the SFT data by its length-normalized perplexity against the initial policy.
Okay.
Then, they sorted the data in descending order. So at the start of each training epoch, the model processes the highest perplexity trajectories.
The really weird out-of-distribution stuff.
Right, the highly complex proof patterns. By the end of the epoch, it is consolidating on low perplexity, familiar examples.
And that reshapes it.
Yeah, it reshapes the reasoning behavior and pulls the model out of local minima without, destroying its pre-existing weights.
We can talk about the theory all day, but how did they actually measure if this behavioral shift was working in practice?
They tracked a very specific operational metric, the validation truncation rate.
Truncation rate, how does that work?
Well, when a model is failing to adapt to long chain of thought supervision, it defaults to those shallow, repetitive loops we talked about.
Right, the spinning wheels.
And those loops naturally hit the maximum token limit and get truncated. So the team used this truncation rate as a proxy for SFT sufficiency.
Ah, I see.
Once that truncation rate dropped below 5%, it basically served as empirical proof that the model had abandoned its shallow heuristics.
It was actually adopting the target-proof search behavior.
Exactly.
So the reverse perplexity SFT lays the foundation. The model now knows how to search for an answer and format a long reasoning chain. But formatting a proof and actually solving an incredibly hard mathematical problem are two very different things. To reach Olympiad levels, you have to scale that capability, which introduces their two-stage reinforcement learning pipeline.
Yeah, real heavy lifting.
The first stage is Course RL. What is the primary objective here?
So Course RL is designed to boost direct solving performance on hard tasks by using highly reliable, verifiable rewards. They utilize a dataset of about 9,000 verifiable prompts.
Okay.
But crucially, instead of using token-level GRPO, which is the standard in a lot of recent reasoning models.
Right, everyone uses GRPO.
Yeah, they opted for Group Sequence Policy Optimization, or GSPO.
Why the shift to GSPO? What makes token-level updates insufficient here?
Think about it this way. With token-level updates, it's like grading a student on every single pen stroke. But with GSPO, you're grading the entire essay. In a complex mathematical proof, a token saying, like, let x equal 5 might seem low value or arbitrary locally.
By 10,000 tokens later?
Exactly. 10,000 tokens later, it becomes the linchpin of the entire logical conclusion. GSPO operates at the complete response level for both reward assignment and policy clipping.
Wow, okay.
It evaluates the sequence as a whole, which keeps the optimization much more stable for long-form reasoning.
That makes perfect sense for massive context windows. And for the reward assignment itself, they used a layered, outcome-based approach. They don't just rely on one simple check, right?
Right. The reward layering is highly compute efficient. They start with high-precision automatic checks, like canonical text matching.
Just checking the final string.
Yeah. If that fails, it moves to rule-based math-verify checks. And only if a sample fails those fast rules is it sent to a generative verifier, specifically GPT-OS 120B.
Wait, so what does the generative verifier do?
The generative verifier is just there to check for equivalent correct answers that might be formatted unusually.
Ah, like if it wrote 0.5 instead of 12.
Exactly.
So now, Course RL has the model reliably finding the correct final answers. But in an Olympiad setting, providing the correct final number with a massive logical leap in the middle gets you 0 points. The logic is still messy. How did they force the model to clean up its actual reasoning steps?
This is the transition to the refined RL stage.
Okay.
The optimization target shifts from final answer correctness to absolute proof quality. They introduced DeepSeek Math V2 as a generative reward model to score the full mathematical validity of the intermediate steps.
That sounds incredibly hard to train.
It is. Because they are targeting incredibly difficult Olympiad queries, they had to introduce two specific memory mechanisms to maximize the learning signal.
Let's break those down. The first memory mechanism is self-refinement.
Yeah, so if a group of rollouts for a query has an average reward below 0.5, the model clearly doesn't know how to solve it directly.
It's failing.
Right. The failed responses are converted into critique and repair prompts and mixed back into the training batch at a 20% ratio.
Oh, that's clever.
It forces the policy to learn the specific behavior of identifying its own logical gaps and repairing them, rather than just, starting over.
The second mechanism is experience replay, which addresses the extreme difficulty of these problems. If you have a query where the model only succeeds on 1 out of 8 rollouts, you don't want to throw away that rare golden trajectory.
Exactly, you save it.
They save it and replay it at a 25% ratio. But they add a fascinating filter. If they have multiple successful trajectories, they select the one with the lowest rollout side entropy estimate. Why does low entropy equal a better proof for training?
Because entropy basically measures uncertainty. If a trajectory has high entropy, the model's internal probability distribution was flat across many tokens.
Meaning it was essentially guessing.
Right, it just happened to stumble into the correct final answer. But if a trajectory has low entropy, the model was highly confident in its logical steps.
I see.
By explicitly selecting the lowest entropy path, they are reinforcing stable, deliberate reasoning patterns.
Hold on, I need to push back on this entire setup.
Okay, go for it.
If they are using an LLM, even DeepSeek Math V2, to grade another LLM's complex proofs, aren't they just asking for a massive feedback loop of hallucinations? We see models tricking LLM as a judge setups all the time by just formatting things beautifully, engaging in reward hacking without actually improving the underlying math.
What's fascinating here is how the researchers anticipated that exact vulnerability.
Really? They saw it coming.
Oh yeah, they instituted a protocol called anti-hack pre-processing. They knew the policy model would eventually figure out how to exploit the reward model's preferences. So before the generative reward model even sees the rollout, the system runs hard deterministic overrides.
Meaning they physically intercept the text.
Exactly. If a generation contains leaked chat template tokens, unbalanced thinking delimiters, or severe text repetition, it is automatically intercepted and replaced with a safe, generic fallback answer.
Oh, wow.
The reward model never actually sees the exploit, so it never issues a positive reward for formatting pathologies. It neutralizes the adversarial loot at the protocol level.
That is incredibly rigorous. Okay, so the SFT reshapes the foundational behavior. Coarse RL scales the search for correct answers. Refined RL hones the proof rigor and self-repair capabilities. The training pipeline has given SU01 all the tools it needs.
It's primed and ready.
But a 30 billion parameter model still has a finite context window and a finite compute budget per forward pass. Olympiad-level problems demand lemma checking, deep exploration, and massive revision budgets that simply cannot happen in a single generation. How do they allocate extra inference compute when a problem is simply too hard to solve in one go?
This leads directly into the third pillar, test time scaling, or TTS.
Right.
The researchers implemented a model-agnostic verification and refinement loop. It operates as a continuous cycle. The model generates an initial solution. Then, it verifies that solution by acting as its own critic, creating a highly structured bug report.
And this isn't just a binary pass or fail check, is it?
No, not at all.
The structured bug report requires the model to specifically identify critical errors, major justification gaps, or minor logical flaws. Then a verdict step decides what action to take next. The stopping rules they implemented are brutal.
Very strict.
A candidate solution is only accepted if it passes verification 5 consecutive times, or it is rejected entirely if major issues persist for 10 refinement steps. And the whole process is capped at a maximum of 30 exploration rounds per run.
It is an exhaustive, self-auditing process, and it demands immense state management. To maintain this loop, SU01 has to sustain coherent reasoning trajectories well beyond 100,000 tokens during inference.
Here's where it gets really interesting. If you look at the specific distribution of generation lengths from the paper's US AMMO 2026 traces, the sheer scale of the text is staggering.
It really is.
The initial solutions hit a median of 106,000 tokens. The refinements hit 83,000 tokens. The structured verification reports alone are around 28,700 tokens. And the final verdicts, a mere 404 tokens.
If we connect this to the bigger picture, these numbers prove a critical point. TTS here is not merely best of n sampling.
It's not just rolling the dice 100 times.
No, it is the explicit, structured allocation of inference compute to rigorous error correction. The model is conditioning on its own massive previous outputs.
It's reading its own work.
Exactly. It is reading its own 28,000 token critiques and then revising an 80,000 token proof without losing the thread of the argument. It proves that a highly curated 30B model can manage complex mathematical state over extremely long contexts.
We have dissected the architecture, the reverse-perplexity SFT, the GSPO reinforcement learning, and the massive inference scaling loop. The final piece of the puzzle is analyzing the empirical outcomes. Did this unified scaling recipe actually achieve gold medal results? Let's start with the verifiable benchmarks.
On the AM 2025 and 2026 benchmarks, SU01 reaches roughly 94%. This nearly matches the baseline of Quen 3.6, 35B, A3B. But the key takeaway is the efficiency. SU01 achieves this with a vastly simpler and highly data-efficient post-training setup. We are talking only 200 RL steps and 340,000 SFT trajectories.
But AM just requires a final answer. The proof-oriented benchmarks are where we see if the behavioral shift actually took hold.
And it absolutely did. On IMO Proof Bench, the base P130B model scored just 33.8%.
Pretty low.
Right. But after SFT and Course RL, it jumped to 76.7% on the basic split. The final SU01 model, running its full test time scaling loop, reaches an impressive 70.2% overall on IMO Proof Bench, which includes the highly advanced split.
Wow.
It is performing rigorous, formal proof generation at a level competitive with models 10 times its parameter count.
Then we get to the ultimate stress test, the official Olympiads. In direct generation, meaning no test time scaling, just a single pass, SU01 already clears the bronze medal lines for IMO 2025 and USMO 2026.
In a single pass.
Yes. It actually exceeds the gold lines for the International Physics Olympiad in 2024 and 2025 in a single pass. But when you turn on the test time scaling loop, well, the results are wild.
Tell them the numbers.
It achieves 35 points on IMO 2025, hitting the gold line exactly. And on USMO 2026, it achieves 35 points, exceeding the gold line by 10 full points. That matches the absolute highest reported human score among 340 elite competitors.
Let that sink in. Matching the highest human score on the USMO with a 30 billion parameter model is a watershed moment for the field.
It really is.
It empirically proves that scaling inference compute via structured verification and refinement can bridge the gap between a strong generalist backbone and an expert human mathematician.
Now, to maintain a completely balanced view of the research, we have to note that the paper highlights specific failure modes. SU01 is not infallible.
No, of course not.
For instance, it failed on IMO 2025 Problem 6 and USMO 2026 Problem 2. The researchers noted that it struggles heavily when it misses subtle structural constraints or leaves gaps in delicate global strategy arguments. Why does it trip up there?
It is a classic symptom of current LLM reasoning limits. The model performs best when a problem admits a rigid formal representation.
Give me an example of that.
For example, it absolutely crushed USAMO Problem 3 by using an ingenious algebraic framework with complex numbers, completely bypassing traditional geometry angle chasing.
Oh, that's smart.
It excels at mapping complex logic into computable spaces. But it struggles with preserving highly abstract, global combinatorial invariants across multiple configurations. It tends to lose the forest for the trees when the problem can't be formalized easily.
Even with those limitations, there is one final data point in the paper that might be the most important validation of their entire approach. It validates the specializable generalist hypothesis.
You are referring to the Frontier Science Research benchmark.
Yes, exactly.
SU01 scored 11.7% on this benchmark. While that absolute number sounds low, it is actually the highest score for any model in its size class. What makes this critical is that it performed exceptionally well on entirely unseen domains like chemistry and biology. Keep in mind, the reinforcement learning stages used exclusively math and physics signals.
The fact that its performance improved in chemistry and biology proves that the RL pipeline didn't just memorize mathematical templates. It generalized the underlying scientific reasoning.
Exactly.
It learned the behavior of rigorous proof search and applied it to completely new domains. It learned how to think logically, not just what to think about math.
That is the holy grail of reasoning models. It confirms that you can isolate and scale reasoning behavior without sacrificing the broad knowledge base of the pre-trained model.
To summarize this incredibly dense deep dive, the collaborative team behind SU01 has presented a masterclass in what they call simple and unified scaling.
Yeah, simple but powerful.
They took a compact 30 billion parameter model. They applied rigorous supervised fine-tuning, guided by a simulated annealing-style reverse-perplexity curriculum to fundamentally alter its behavior.
They completely rewired how it approaches problems.
Right. They scaled that behavior through a two-stage verifiable and generative RL pipeline using group sequence policy optimization. And finally, they amplified the model at inference time with a meticulous verification and refinement loop capable of managing over 100,000 tokens of context.
The core takeaway for our listeners, the ML professionals, researchers, and data scientists, is that the brute force paradigm is no longer the only path forward. You do not necessarily need 500 billion parameters to reach frontier-level reasoning.
You just don't.
A highly curated, intensely data-efficient post-training pipeline, combined with intelligent test-time compute allocation, can drive a compact model to top-tier human performance levels. We are looking at a triumph of data quality and optimization architecture over raw scale.
We are no longer bottlenecked purely by the size of our computing clusters. We are limited by the precision and quality of our training recipes. So what does this all mean? I want to leave you with a thought to mull over. If this exact, highly efficient recipe using just 340,000 SFT trajectories and 200 RL steps can push a 30 billion parameter model to match the absolute highest human score on the US SAMO,
Yeah.
what unprecedented emergent capabilities might we unlock if we apply this exact unified scaling recipe to a 400 billion parameter dense model?
That's a staggering thought.
Or better yet, what happens when we apply this rigorous, structured proof search behavior to completely non-STEM domains like formal legal reasoning or strategic policy design? The blueprint is here. The question is, where do we point it next?